someone can check. I need to mute the game sound though. Or at least turn it way down. Alright. Then connect the broadcast. Alright, just
I don't see you.
So we... What? You don't see me?
Are you streaming already?
Yes, I'm streaming already. Am I not streaming to Twitch?
Yeah. Yeah, no. Now you are, yeah.
Alright, yeah, it's a little delay, of course. Okay, then... let me post the on-air button, the on-air message. Oh, I need to switch the restream title. Forgot to do that. Why does it still say Orbit Rescue in Discord for me?
What do you mean?
Now it changed. It switched already. The song's still not finished. Alright, yeah, for all the Twitch viewers that are there already, we'll be starting in just a minute, waiting for the current song on the radio to finish, as you might hear, and, yeah.
Oh, do we have viewers already?
Oh, we're live now. You can go.
We are live on radio.
Yes. And on Twitch, of course.
Cool.
So, welcome everyone.
Hello everyone, this is Nightfall Zero, live from the Red Comet, and here with me is that Michael, live from...
Hello.
What is the name of your ship again?
My ship is the Twilight Shepherd.
Twilight Shepherd. That sounds so emo, but it's alright. And anyway, guys, welcome to the newest episode of Dangerous Cosmology, and of course, together with me and that Michael is our guest of honor, our Dr. Commander Shoba.
Hello, good evening.
Welcome back. Thank you for your time again. It's only me and that Michael today, live here as hosts, but we got quite a few questions. The topic today will be time, but before getting into that, I wanted to ask you, how are you faring with the next waypoint? Did you get there yet, guys?
I just barely got the one last week. I haven't started on the latest one yet. I'm still chilling at waypoint 3.
I'm still a little bit away from waypoint 4, so I need to catch up quite a bit.
Well, there's quite a few interesting points of interest. At least I found them interesting. So the galaxy is starting to get quite dense in terms of stars as we're getting close to Colonia. So there's quite a few interesting views. But yeah, this show is going to hopefully provide some comfort to all the people out there exploring in the black or providing support to other pilots with fuel and repairs and stuff like that. So together with music, as we do every week, we're going to bring you some science. Last time we spoke about the CMB, cosmic microwave background. This week the topic will be time. Last week we went for about 2 hours. We will try to keep it a bit short today, because we were a bit burned out last time. But we will try to answer questions. We got quite a few of them past couple of days, but we will take them live as well. So if you're listening in and you have questions, feel free to drop on the Distant Radio Discord channel, server interview questions channel, and drop your questions there. We will be taking them live and answer them. They don't have to be strictly related to time, but if possible, we will prioritize questions concerning today's topic. So let's just cut to the chase. Time. What is exactly time? Because we experience it every day, of course, but at least I speak for myself, but when I stop and try to think exactly what time is, I kind of get stumped, because it is something so ingrained in our everyday life that even trying to describe it is hard. We can't really conceive anything outside of time. So the question is, how do scientists and in the specific cosmologists like you, Shoba, consider time? If someone would ask you the question, what is time to you? What definition would you give?
What is time to me? On a personal level, time that I don't have to finish my deadlines.
Yes.
What is time to me as a cosmologist?
I know you're busy, and I know we're taking away time from you.
That's not what I meant. Not at all.
It is what you
don't
meant.
Worry.
It is what you meant. We know.
Time as a cosmologist, especially working at the fringes of highest redshift, like we do, it's a bit of a nuisance, really. Time delay between something happening and us seeing it complicates a lot of things. It adds a lot of uncertainty. If only we could see things live, things would be easier. But at the same time, it's fair enough that we get a time delay for our observations. It allows us to see things from far in the past. So that's quite convenient to trace the history of the universe. But in terms of our work, time is just something we have to put up with.
Okay, but apart from that, do you have because as far as I know, time as a concept originated at the Big Bang. There was no such thing as time before the Big Bang happened.
If the Big Bang is taken as a singularity, then yes, absolutely. There was no time back then, and the most dense the energy density was, the more space-time was curved back then, the slower time appeared to pass for those particles, if in case you have a singularity. But of course, we haven't completely ruled out other models, such as the Big Bang happening as a bubble within a bigger thing, maybe universe bubbles that are born in Big Bangs and grow and then eventually crunch back. These models have not all been ruled out yet. So saying for sure that time started at the Big Bang, observationally, that's not quite true. But it's true that what is true is that in these theories, in any theory that relies on a true singularity as the start, then your notion of time becomes very, very dodgy. It's not really well defined anymore.
Okay, because we often hear that time is pretty much a fourth dimension.
Yes.
However, it is obviously not the same as other spatial dimensions because we can't really move through it.
Right. Professionally, as a cosmologist, time is a dimension just like the others with only one difference. So time going forward is the reason that gravity attracts in the same way as the bending of space is the reason things attract. It's really space and time both bending, creating gravity. But the comparison kind of stops there, because obviously they bend in different ways. Time always goes forward, while space can go both forward and back. You can move in space, but you can't move through time.
But isn't that... I mean, time moves forward according to our perception, simply because we
That's
can't...
what I wanted to say.
Yeah, because we just can't... We can move forward and backwards, but in a special dimension, but we can't move forward and backwards in time. We are going towards one direction that we call forward, but I assume that's an arbitrary way to call it. We could call it backwards and it would be the same thing. If you invert everything, it's just a label that we put on it. We just keep going in one direction without the ability to revert it. So everything we see, including spatial phenomena, are obviously influenced by this direction we're going forward, right?
Yes, in a way, the way we define the arrow of time, what's forward and what's back, that is definitely based on our perception. And actually, if you want to define in general relativity what is forward and back, you kind of have to define forward is the way we see gravity attract, forward is the way that entropy increases, and we only see it in that direction. But even in GR, there's a reason that time is special. So when you write down your metric, the basis of the space-time you're trying to describe, all the spatial dimensions have a plus sign and the time dimension has a minus sign. And that really causes it to have a directionality. You can't move in both ways in it. It's not the same type of dimension as space. It has a special status, even in GR.
Okay. Yet there are some situations where time is influenced. It is either like... I'm not sure I'm using the correct terminology here, but time can be contracted or dilated when you have time dilation. When you approach speeds close to the speed of light, time actually stretches. So it is not an absolute constant. It is, for all intents and purposes, an actual dimension that we can technically travel through. We can't really control how, but...
This property of dilation and contraction happens for space too. So that's a property that happens to all dimensions, no matter their type. But there's still different types of dimensions. So length contracts too.
Is
Sorry, Michael?
time only one dimension, or could there be more than one dimension for time?
That's a great question, actually. So we don't really know. For a long time, we thought that if we included in GR, if you take general relativity, you take your 3 dimensions of space and 1 of time, and you just shove another 1 of time in there, we used to think that would basically break all our predictions, that things could not conserve energy in both time dimensions at once, more or less. But it's still being taken reasonably seriously, having 2-time physics, as we call it. And that's motivated by a result from string theory, actually. That in string theory, some models are more stable than others if they have a certain number of spatial dimensions and a certain number of time dimensions. So these 2 types, you can have varying numbers of them. And a popular one, I think it's M theory, F theory. One of them has 2 time dimensions. So when we figured that out, there's been a lot more research in that since then. And we think, maybe having 2 might be stable, but it's all extremely
that idea, I thought that
theoretical.
idea of mine actually was a brain fart, but I didn't think it actually had some base in science. So,
yeah, it's being looked into
amazing.
quite seriously. Yeah. Surprisingly, the result about causality is still quite unknown. So causality is that the things we perceive as we go forward in time always have a logical source in the past compared to us. So things result from something that is in the past. It's in their light cone, so it can affect them. So things are causal and things are local. You can't have action at a distance. And these kind of things. And if you want to preserve that, The fact that we see the universe being causal in one time dimension might mean that the other time dimension is not. And so like non-causality is pushed into that one to preserve this one. And it makes sense. But it's very early days.
There
Very
are
early
just new
days.
questions forming in my head because, yeah, the topic of time is just so extensive. But we should get on with questions about from people.
Yeah, indeed. And concerning questions, just so that everyone is aware, I'm going to repeat that we are taking questions live on both the interview questions channel on the distant radio server and the astronomy channel in the on the FleetCom server. So just hop in, write a line if you have questions, and let us know. So we're going to start. You know, I'm starting to regret having picked this topic because I'm already confused by everything. I thought it would be cool, but I expect it to be quite complex and convoluted.
Yeah, it's hard. And I have to say, I did a bunch of GR and quantum field theory in my master's degree. That was 2 years ago. That's what I'm going off of. If it's cosmology specifically or black holes related, that's easier.
I know.
I'll probably still know a bit, a fair bit. I'll do my best.
Well, you probably still know better than us, know more than us. So even if it's not your exact specialization, you probably can clarify some questions that our listeners have. Starting from this one, let me see. So it's actually from you, Michael. You were asking about... Well, I mean... Yeah, it's a bit weird. You were asking if time could be just another wave function, and
Wave
that
function.
I don't think that's.
I'm not sure that's a question that makes sense. I'm sorry.
Hey,
yeah,
he asked
exactly.
you asked it.
Yeah, I asked it but to determine that we actually have to make sure if time is incremental or even something more tangible, like some sort of what's it called, particle.
Yeah, no, I mean, your question was a bit weird because you said...
Oh, I see what you mean. Okay, I get it. You're talking about if it's quantizable, if you can make it into small chunks.
Yes.
Because if it's continuous, it's really like a wave, but it could be quantized at the same time, so kind of a parallel to quantum mechanics. That's a good question. That's a good question.
Yoo-hoo!
And they're all good questions, and they all have really
questions.
difficult answers. Could time be quantized? The short answer is that we don't know. It could be. There's an interesting disagreement between quantum mechanics and general relativity, or more specifically, beyond quantum mechanics when we moved on from quantum mechanics to quantum field theory. That still has very strong disagreements with GR in some ways, but quantization isn't one of them. So even in quantum mechanics, not everything is quantized, right? A lot of things are, like energy levels in atoms. When you put an electron close to a proton, it can only sit at some distances and no other distances, in terms of energy levels. But some things, even in quantum mechanics, are not quantized. So if I take a strip of metal or anything, like a bunch of gas, and I heat it, and the electrons stop being bound to the protons, and I say, okay, now in this box of gas, where are the electrons? It's continuously everywhere. In that case, the quantization goes away because it's not being acted on by attraction anymore. So if you ask the question, where is the electron after it's left the proton? The answer is continuous. The wave function is continuous over the entire box size. So in that sense, space isn't quantized. Even space, not even time. And actually, space being quantized used to be a thing in quantum mechanics close to its beginning, before we moved on to QFT, quantum field theory. Because basically, you needed to assume a smallest spacing of time called the Planck distance in order to make some equations work. Otherwise, we couldn't get the answer out. But then when we upgraded, so to speak, to quantum field theory, we didn't need that trick anymore. We have better, much more complicated tricks to make our equations work now. So even the the assumption that the Planck length is the smallest length, even the quantization of time has of space has kind of gone away. It's not to say it isn't. It's just to say we don't need it to make quantum mechanics work anymore. That's the short answer. And then the disagreement with GR, obviously, is if space is quantized, if you really have a smallest amount of space, but at the same time in GR, if you're accelerating, space contracts and time dilates, then these fixed quantities cannot really be fixed. If there was a smallest amount of time that exists out there, and everyone else was just seeing the wrong one, that would mean there's a preferred frame of reference in a way. So say there is a quantum of time, then everyone on Earth doesn't see that. They see a longer one because the gravity of the Earth is slowing down time slightly for us. So we would not agree that this is the smallest amount of time. Everyone would disagree on what it is. And if there really is a final answer, it kind of means one frame is better than the others, which, GR isn't keen on because all the frames are equivalent. So we don't need it. It might cause a few problems, but we can't know for sure until we really unify GR and quantum field theory.
Okay, I probably understood 10%. I understood 10% of what you said.
Oh no, I tried to be clear.
No, it's just me, just being stupid. Don't worry.
Yeah, I would need to research that as well to get a better.
I mean, we are recording this, so we can listen it like 10 times, to make sure that we understand properly. Like when you're reading a hard textbook, you need to reread the same paragraph 10 times.
Sorry, I'll try to.
No, it's not your fault. It's not your fault. But Michael also asked something. Yeah, I mean, you also asked something about if the relativity of light speed indicates that we are living in a simulation. What do you mean by that, Michael?
Yeah, because if any mass approaches light speed, time slows down. And
it looks like lag.
Could be because of exactly, lag, because the processing power can just handle so much if it's in a simulation. I think was it Elon Musk who originally had that idea?
No, he really didn't. Elon Musk never had an original idea.
Okay.
Sorry, Musk fans. He's great. Yeah. Don't take me wrong. I love him. No, he didn't come up with that.
You can't do everything.
I don't know. I think that sending a car to space is original.
Yeah, okay.
So,
but did he really do it, or all the engineers? He funded it. That's good. Okay, fair enough. His rocket designs are kind of clever.
Department told him to do so. Maybe. Anyway, I heard of the idea that light speed might be the limit of light speed and time. Time would be an indicator that some sort of processing power is involved, and that might have a limit.
That is a very cool interpretation, but I'm not sure anyone's seriously working on that. There's other very good reasons why that's been suggested, though. And an interesting anecdote: when we run simulations of the universe, so we have these big simulated computer boxes, and they call them boxes because the space is a cube. When we simulate them on supercomputers, we actually can't resolve the speed of light. We have the same problem. If you have things at the speed of light, we miss the action. Basically, it travels too fast, and we can't keep track of it. So we actually use the reduced speed of light approximation to make things work. So, that is a trick. It works if you want to run things and you don't have infinite resolution and infinite power. So it's a real thing. It's very interesting. I mean, it's very cool.
To say the least.
Yeah, definitely very cool.
So let me just, because sorry, what?
Ask questions not posed by me, because
because your questions are stupid. Okay.
No, there was a good follow-up from that. Why we think the universe might be a simulation. It's not only the finite numbers of things like the speed of light and or the quantization of space, which may or may not be a thing. I mean, you'd think if you were trying to simulate three-dimensional space, you would at least make all your tiny pixels have constant sizes. Allowing them to dilate for different observers sounds a bit too complicated, A Newtonian universe would probably be much simpler to do.
Yeah,
But
maybe
anyway,
that is just a bug because the simulation isn't perfect.
Well, I
Well,
guess
who
we
knows?
just have to wait for the patch then, because
yeah, no, but there is something to it. I mean, you might have heard. I think last summer it made the headlines again. This holographic principle vision of
Yes.
the universe. Have you heard about that?
I have not.
So the holographic principle, basically, if you strip away all the complications, is that our space-time, our 3 dimensions of space and 1 of time, is surprisingly compressible in terms of information. It can actually all fit in a 2D drive. So including everything. The 3 dimensions that we know are not fundamental. You can encode the information in a purely 2D way. So one of our dimensions could be kind of a projection from the other 2. There's no unique information in the 3rd dimension, and that's the conclusion that comes from black holes. Strangely, that's how we discovered this property.
That's still a hypothesis, though. It's not.
Well, it's either that or we don't understand entropy around black holes, which that might be also be true.
Well, speaking of entropy,
Yeah.
this is actually a follow-up that I wanted to ask. I just came up with this question. So if gravity influences time and space, but we're talking about time, so if gravity somehow influences time, and you earlier defined that time is what we put, what a label that we use to, among other things, indicate the constant increase of entropy. Does that mean that gravity also influences entropy? Because I thought that entropy is pretty much there to stay.
Does
Because
gravity affect entropy?
if time is the increase of entropy and time is influenced by gravity, we can influence entropy by,
No, I don't think space affects entropy.
No, I'm talking about gravity. Because if time dilates or contracts, also entropy does that. Does the same because it follows time.
To some extent. To some extent. So what happens? Let's say you have a gas that has some amount of entropy and is falling into a potential well. Its gravity will decrease because is that right?
I don't know.
It depends how you measure entropy. Let's see. I don't think it's that clear. I don't think space-time bending affects entropy one way or the other. It depends what you do with it. Space can do both. So you can compress things and you can dilate things, and compression and dilation will have effects on entropy. But it will depend on what you're doing. While time can only increase entropy if the rest is held constant. So it doesn't do the same. There's no direct link there.
Okay, just to give a quick explanation, and I want to actually show off myself to show everyone that I know something about science. Entropy is the tendency of everything to go from an order state to a disorder state, right?
Not quite.
Of course,
Yeah,
and
no.
I can't even show off because you have to contradict me.
Almost. Entropy just means amount of chaos, amount of disorder.
Yeah, that's what I meant.
Well, the law that says it can only increase is a law, not entropy itself. It's like water isn't the same as saying water's wet. Like entropy is just the amount of chaos something contains. In some cases, it can decrease. Right? If you have a very messy room and you tidy it, entropy has gone down.
I mean, in a closed system without an influence from an external force, entropy tends to increase.
It can only increase, yeah. If it's left on its own with no input of energy, it can only increase.
It will increase, period. It will not stay stable, it will not decrease.
It can stay stable. In some cases it does, like quantum mechanics, definitely entropy stays the same over time. You put an electron around the proton, it will stay there. It will not go anywhere. It's not increasing or decreasing. In quantum mechanics, there is no time in that sense.
No, but we do see it in the larger scale.
Yep.
And in our everyday life.
Yep.
So, of course, if we go into quantum mechanics, things start to get weird, but in terms of the universe, in terms of what you do as a cosmologist, entropy is there. You can't really ignore it. It happens.
Well, it's what drives all of physics. The reason stars are emitting light, the reason gas behaves the way it does, and planets go around the sun in a way.
Exactly. So entropy is this tendency of everything to... Okay, I'll just shut up. You can say it.
Entropy isn't a tendency. Entropy is a property of stuff.
Look, I'm just trying to
no, it's
trick listeners to that they may believe that I am at the same level that you are, because otherwise.
But no, it's just entropy isn't a tendency. It's just a property of stuff.
Okay.
Like a number. You can put a number on entropy. This star has this number entropy. You can do that. It's a number. The property that it increases is a law that is usually true. Although if you go to weird things like black holes or the universe as a whole or quantum mechanics, is not that simple. That law has, asterisks next to it.
Right.
Entropy is just a number that you can put on a system.
Okay. And entropy is directly linked with time.
Yes.
By definition. Because if you stop time, you also stop entropy.
Because we define time as being increased entropy in a closed system. It's a definition.
Exactly. So this goes back to my earlier question. If you stretch or contract time, you also stretch or contract this number of entropy, this law of entropy, however you want to call it.
Yeah, but remember, it's in a closed system. If you start to contract and dilate time, it means you're accelerating. If you're accelerating, there is some sort of energy change going on. So your law of entropy isn't going to behave simply anymore once you doesn't have energy exchanges. And so it's not really that simple. The thing is, gas can move in time, even when it's not moving in space. It's like you at your desk. You're not moving in space, but you're still moving in time. But you can't do the opposite. You can't move only in space and not in time.
Well, in that example, we are technically moving because we are rotating, but I get...
We're in your ship. We're moving compared to that star, but yeah.
I understand your example. I understand your example, but okay. All right, I will just nod and pretend I understood everything, and we'll just move on to the next question, which is not from Michael, surprisingly. It is from Pookie, actually, who was here last week, but she is not here now. She's asking, well, we know how Earth time works, in a sense that we measure it. Assuming that we go all at the same speed, we have clocks that can more or less accurately measure time, which is the same for everyone, for every human on this planet. She's asking if there is such a thing as a stellar time.
Ooh.
Or space date, like
Star Trek.
like Star Trek, exactly. Like some sort of universal time that you could use if, like now, if we are journeying through space, how can we organize ourselves and to have common frame of reference to say, okay, next show is at 1200 hours, if we don't have a fixed frame of reference? Is there an actual fixed frame of reference in the universe that no matter where we are can be used to define, to have a fixed point in time so that we can calculate it for everyone else?
Yes, absolutely. I mean, you can pick one. So none of them is preferred, but it's always okay to pick one. And then everyone can compare their local clock to that clock that you've picked and adjust their clock to match it. It will actually be pretty constant for inhabitants of planets. I think surface of the Earth. Okay, so the closer you are to something heavy, the slower your time moves. So on the surface of the Earth, our time is passing slightly slower than someone up in space. That means we're aging slightly slower than they are, right? There's a small shift, but it's a very small shift. So say we decide to pick a point where there's almost no gravity in the Milky Way, like really far away from many, many stars, maybe in the halo somewhere, above the galactic center, quite far away, I don't know, like 20 megaparsecs up, something nice and comfortable, when you're not affected by being close to something heavy.
Yeah, they're very comfortable, yeah.
If you can get there. That would only be, what? If you wanted to adjust your Earth clock to that clock, to adjust for the fact that our time would be moving slower, you'd only need to adjust it by... how much would it be?
I don't know. Are you calculating this now?
Yeah, in my head.
Okay.
Show off.
Just say a random number, no one will check.
1 second every 50 years. Ish.
That's not a lot.
So,
Don't quote me on that. It could be wrong by a factor of like 10. But,
okay.
you know,
Close enough, I guess.
close enough. Roughly, you'd have to adjust it by 1 second once every 50-ish years.
Which is not different than what we do on this planet, well, on Earth, when we have to, like when we have months with an additional day, or we add a second every year to adjust for this, for the discrepancy in clocks.
Yeah, because there's a few effects. So the Earth is kind of slowing down its rotation, plus the number of times we go around the Sun isn't an entire number of days. We actually end the year a bit wrong every time. By the time the Earth goes back to where it was at the same point in the orbit, it's not the end of the day. It's like slightly off by like 4 hours, I think. So we have to adjust it once in a while. So this correction would be way smaller than that. And then you can tune in to, I don't know, neutral galaxy time.
And that is going to be universal, no matter where you are.
Well, you define it. You have to pick one. Someone in Andromeda might not agree, because Andromeda is moving towards us, plus the gravitational field is a bit heavier. So there'll always be a slight error. You can't really pick one where there is zero gravitational fields, because gravitational fields extend to infinity for all of space. So there's no place in the universe where you can go where there's no gravity. So it's not universal, but it's convenient to pick because it's Milky Way universal.
So as long as you pick one and everyone agrees,
yep,
you can just coordinate your clocks.
Pretty much. And it's not even a big change. Unless you care about nanoseconds and stuff like our sat-navs do. GPS has to be corrected.
Okay, so the concept of...
nanoseconds matter.
Yeah, nanoseconds matter. Light travels a long way in a nanosecond.
So the concept of astral date is a thing. It could be a thing, in Star Trek.
It's convenient to pick one, for sure. Yeah.
Yeah, it's probably easier if we're a multiplanetary species to have some general central time instead of Earth time.
Damn, timekeeping of multiple planets would be impossible. Can you imagine if they had different day lengths and different months?
I mean, I struggle with time zones already.
I mean, have you seen the Martian calendars that they've proposed?
Yeah,
they've come up with Martian calendars with different number of months, because it's not the same. It's Mars.
Of course.
So January has no meaning for them. That's already complicated if you want to coordinate with a Mars colony.
I can see wars happening because of this.
Our calendar is better.
Exactly.
But it makes no sense to use on Mars.
Mars would have to change the name of March to something more Earth.
More PC.
Because...
What do you mean?
Because March is named after Mars. So on Mars, this month has to be named after Earth.
Oh god. That would be so cringy.
Just to add to the confusion.
Unintended confusion consequences. What were they thinking, calling them after planets 2,000 years ago?
Right. Okay, so hopefully Pookie will hear this answer once she's back online and will hear the recording. We'll move on to the next question. We are receiving some live questions. I am seeing them, guys, don't worry, but I would like to follow the order which received them, because we may have those listeners on. And the next one is from Rusted Bulk Mike, and he actually wants to add to Pookie's question. And we already answered that, so I'm not going to read that because I am dumb. So ignore me. I'm so bad at hosting. Michael, you should really do my job because I really can't.
Well, you're way better than I am.
Right.
You're way more secure in talking.
Sure. I'm just better at bullshitting, I guess.
Also, I need
That's
to
a
make sure I
skill
don't
if you're a
crash that
radio
now.
host.
Yeah, we received some questions that are not related to time, so I'm going to skip them at the moment. If we will have time at the end, we will answer them. Now, let's go to the live ones that we got a few minutes ago. We have one from Scaleus. He's saying that, of course, our eyes capture light, etc., to create what we see. So if we could theoretically travel faster than light, mess with it and go back. I'm not sure what you mean by mess with it, mess with light. Would the object appear to have changed, even just for a split second? Could you theoretically use this to permanently change something? So I'm not sure I understand the question. I'm not sure if you understand, Shobo.
I'm not sure if I understand.
Basically, he's asking if we theoretically go faster than light,
Sure.
mess with it, I guess, with light. Sorry, I'm just rereading
I think
this.
the question isn't formulated correctly because I think it's missing some words or context.
Yeah.
Well, even if you could go faster than light.
Well, he's typing now, so let's just wait. In the meantime,
the frame of reference will still be with respect to you. So with respect to you, nothing will appear to change if the thing you're moving goes at the same speed as you, no matter what speed you go at. That's one of the fundamental concepts of GR and just physics in general, really, is if it's in your frame of reference, it doesn't change with respect to you.
Okay.
So maybe that answers it. I don't know.
Well, I don't know. I mean, to me, that question is a bit weird because the assumption is that we go faster than light, which makes it already invalid because we can't. So I don't think that there is a scientific explanation of what would happen because that is just not a thing that can happen.
There's a bunch of theories, but not really.
I mean, it's really something that breaks speed of light. I guess it's up for grabs. I mean, correct me if I'm wrong, but of course you can't experiment on this, or even I think even math breaks down if you try to do something like that because it's just not possible.
Maths is kind of okay with it. Maths is okay with a lot of things. It's just about finding out which models that work with maths actually happen in real life. So I think everyone's heard of tachyons, particles that can go backwards in time.
I thought they were fake. I mean,
fake.
Like they're not. They've never been seen, or
no, of course they have never been seen because if they actually existed in this universe, everything would break down. But in terms of maths, they fit in snugly with the other particles. They're okay.
Would be particles that went faster than light, but I think the result would be the same.
The result would be that you'd see some things happen without an immediate reason. So it would break causality and locality. It would break everything. And our universe has never been caught in the act of not being causal. Everything was caused by something nearby and in the right time order.
Don't singularities break causality? Because if black holes break time according to GR, which means they also break causality.
No, not really. I mean, inside the black hole ergosphere, some things would be strange. But in terms of GR, actually, it's fine. Because what happens is that only the things in what we call your past light cone are allowed to affect you. So if something isn't in your past light cone, it can't affect you. That's how we define locality. So if any event has to be a consequence of something that happened in your past light cone. So what happens inside the black hole ergosphere, where these lines of time kind of wrap around themselves, it's not that something outside of your light cone can suddenly affect you, like would happen with a tachyon. It's just that your light cone kind of wraps all the way around to itself, so your future is also in your past.
Okay.
It's that kind of messing with time, but GR still allows it. It's not that it doesn't exit your light cone. It's just your light cone bends to be unrecognizable.
Right.
Well, tachyons can just travel wherever, so they don't have to come from your past light cone. If they can go faster than light, they can just end up, anywhere at any time. And that's never been seen. Everything had a reason from its past light cone. Every event that we've ever observed.
Okay, so even inside a Kerr black hole, causality is not broken, you're saying? It just bends.
Yeah, causality is bent, but it's not broken.
Okay. So that's the thing. Causality cannot be broken according to what we know in any circumstance.
In GR, absolutely not. In quantum field theory, people experiment with messing with it a bit. It's complicated. We should have a topic about quantum mechanics for that.
If you're willing, we can make one of the next shows about quantum mechanics. Yeah, it's not exactly cosmology, but if you're confident with it.
Yeah, I taught it briefly, so it should be okay.
Okay, well, yeah. I mean, if there is enough interest, we will ask. If there is enough interest, we will definitely make a show about it. But in the
faster than light travel probably doesn't happen because we would have noticed it by now if tachyons actually existed. If they could be produced naturally, at least as particles that just exist, and most particles that can exist as a rule.
I guess.
So probably we would have noticed by now, but we're not entirely, not 100%, but probably not.
Okay. Well, as a follow-up to the previous thing we talked about the frame of reference, I mean, I suppose the answer to this question is going to be yes, but I'm going to ask you anyway because I'm usually wrong. Shaggy Dog is asking if we could use he's asking if is this universal time can be the distance from you to the point of the Big Bang. I assume that he means the CMB because that's the farthest thing in quotes that we can see.
The question was in relation to Pookie's and Mike's question.
Yeah, exactly. Yeah, it was a follow-up to that. This is why I said
yes. The answer is yes. It can be with respect to anything you want, and actually that's something we call proper time in GR. If things are moving around along their preferred geodesics, that is the way that they want to move naturally and they're not interfered with, they will follow a natural progression through space-time. And then along those paths, you can define any distance that you want. There is no problem with it. Actually, when we talk about the age of the Big Bang, well, the age of the universe, or the time ago that the Big Bang occurred, that's the kind of time we use. Because in cosmology, you have to be careful what you mean by distance and what you mean by time, because depending on how you look at it, there's different answers.
Well, that actually brings us to another question that the same Shaggy Dog asked. That can time be described as the same thing as space? Because we say space-time. So basically he's wondering if in certain circumstances they kind of merge in a sense.
Oh, they're always merged. You can never move on.
No, of course they're tied, but they're not the same thing. Okay, in normal speaking, time is not space. However, we often heard in sci-fi and even science the term space-time.
Yeah.
So are there some situations where they're not just tied, they're literally the same thing?
No, they're never literally the same thing. Never. So they're both called dimensions. In general relativity, that has a very specific meaning. It's to do with how many elements there are in your matrices. When you have to do all your equations, you need 4. But they're fundamentally different even in the maths. Time has the opposite sign, has a minus sign in front of it that distinguishes it from space. They can never be exactly the same. But they have some properties because they're both types of dimensions. For example, they contract and dilate. When you travel along your world line, you're always traveling through both. So you usually you have to consider your movement from all of them for things like conservation of energy to make sense. You can't really take one without the other. They are tied and they exchange lots of information. They bend. Matter bends space-time, and space-time tells back mass how to move. So they are linked on every level. You can't affect one without the other.
Okay.
But they're not the same. They still behave differently in some ways.
All right. I think that answered the question. Now next, I'm taking them live, so I'm trying to read them as I speak, but I'm not rephrasing them. So some of them may be a bit unclear. So we'll have to ask you guys to clarify them. We have one from Hoyer M. And it seems to be a follow-up to one of the previous questions. He's asking, what's the smallest possible unit that we can say that time exists? I'm not sure if he's referring to the Planck time, if that's even a thing. I think you mentioned
it's
Planck
linked
distance.
to what we discussed earlier.
Exactly. And you mentioned, Shoba, that time is not, I mean, this is what he's saying. You mentioned that time is not relevant on quantum level. I'm not sure that's exactly what you said. But I think he had a bit of a disconnection, so he didn't catch the entire answer. But again, this recording will be uploaded, so if you guys missed any questions and you want to go back and re-listen to it, you will be able to do that as soon as we are done. Michael will edit the audio and will be uploaded and rebroadcasted probably. What do we know?
Exactly. We will.
What?
And also
Yes.
we will share it on
Okay, cool.
on a site to listen to.
Yeah, exactly. And last week we didn't manage to have a Twitch stream, but now we have. So if you guys prefer to listen to this on Twitch as you watch Michael doing things, I don't know what you're doing on your ship now. But
I'm traveling and exploring.
Cool. So yeah, you would be able to listen to that. But yeah, basically, I guess that time gets weird on a quantum level. This is pretty much what he wants to talk about. He's saying at which scale time moves too slowly to matter in any way, I guess.
Yeah. In terms of quantum mechanics, we have that threshold, that is true. So I think what he's referring to is that in quantum mechanics, at the very base level, in things like atomic transitions and particle physics, there doesn't seem to be such a thing as time, because entropy will not progress, it can stand still. So as we mentioned before, if you have an electron around the proton, it will not move in any way. It doesn't have to increase its energy level just because of entropy. So in that sense, it doesn't really experience time in the same way that we do. Although some things are still affected at the quantum level, like decays, like if it's around a neutron, say, that neutron will not be stable forever. Eventually it will decay into a proton, I think, unless I have it backwards. Well, one of them decays into the other, given enough time. So time does have a meaning in quantum mechanics.
Okay. Well,
but what he meant was about scale, right? So in addition to these caveats that particles can decay over time, which is one way that quantum mechanics has time, it's also a scale thing. So you might have noticed that everyday objects don't behave in a quantum way. You know, they don't diffract. You can't pass through walls in the way that particles can pass through walls.
Yeah.
And there is a threshold that we say if you're above this, all the quantum effects have kind of picked a side. So quantum physics works by different states coexisting. It's one or the other or both. And above a certain scale, they all interact with each other, and the quantumness kind of breaks down. It's what we call decoherence. So you can raise it quite high if the thing you're studying is small enough, but I think the largest we've gotten it is a small microbe. We can get small microbes to still be kind of quantum. So if you translate that into time, you can have a frequency for the size that this maximum thing is, and from that you can deduce a typical length of time, which would have kind of the same effect. So a threshold below which quantum effects are much less important.
Okay. Well, I guess that there is an interest in quantum mechanics, so we will definitely make a show about it. So we will definitely talk about these things more in depth if you are willing.
Yeah, I have a lot of questions for quantum mechanics too, so
well, keep them warm.
I'd be happy to. Yeah,
Keep them warm, because I'm sure that there are other people interested. But going back to what Scaleus said, we're almost out of time, but we're going to try and answer what we received. Okay, basically he was implying time travel. I didn't want to go down the rabbit hole of time travel, because that would require hours and hours of talking, because there's a lot of theories of whether it is possible or how it would work. Right. I wanted to keep this debate, this talk about time, more grounded to actually what we know currently, rather than speculation. But just to answer this quickly, he is saying... okay, let me just read this again to make sure I understand it properly. Help me out, Michael. So basically, if we could time travel, but based on temporarily changing the way we interpret something using light, he is saying if we, for example, are we looking at a wall and somebody walks in front of it, you wouldn't see the wall anymore. Okay.
Yep.
And that's all right for now until here. What would happen if you change the arrangement of light to appear as something else?
Oh. No, you wouldn't. That wouldn't change time. You're allowed to play with light as much as you want.
Okay.
It won't affect the passage of time. Light has this special place in general relativity that is going at the maximum speed. So from the point of view of a photon, if you were a photon, no time would pass for you. Time doesn't really exist from the point of view of the photon. So that's one thing. Second thing, if you just change the way you see things, it wouldn't allow you to get photons from the future. You couldn't see the future or anything like that. You can play with photons at the speed they travel at, and even bend them in ways to hide the things that are in front of it. To be fair, that's what mirrors do. Right? Someone walks in front of a wall and you can't see the wall anymore. Well, if you had a series of mirrors to make the light go round, then you can see the wall and the person. And there's no paradox there, it's fine. So changing the way light travels doesn't affect where it comes from. It still has the same maximum speed. And if you were going faster than light, then sure, things would start to break down. But
okay,
they would break down in many, many ways first. Sure, you'd see weird optical illusions, but I think you'd have bigger problems by then.
Yeah, I guess so. We have another follow-up by Hoyer Ram about tachyons again. He's mentioning that why should we have already seen tachyons already if they existed?
Because
he is asking, are they on current accelerators' energy levels?
Oh, even if they were. So he's saying, okay, we haven't seen tachyons yet. Maybe it's because they haven't been produced yet, because all particles have an energy, and you need to manufacture enough energy to kind of crystallize particles out of it. Yes, you do, but tachyons can go backwards in time. So even if you became able to produce them at some point in the future, they will come back here, right? They would go in all directions. So even if they became possible in the future, they would go back in time when we would see them today. Plus, at the time of the Big Bang, in the first 5 minutes, we had way more energy back then than any accelerator we will ever build on Earth. So in those first instance, where all particles in the universe crystallized out of pure energy, they would have taken every available particle shape. So you would have had a ton of tachyons if they were a stable form, you would have had a ton of them, and they would have traveled pretty much anywhere in time that they wanted to.
And we would have seen them.
Most
or
likely.
detected them. But according to the maths, would they have mass?
Negative mass, I suspect.
Whatever that means.
I don't know what the current surviving theories with tachyons are. I think a lot of them are dead. But depending on how you fit them exactly with the other particles in their happy family of particle
How could you
physics,
even detect negative mass?
you wouldn't. So if you produced a tachyon by accident in an accelerator, you would just see all this energy disappear. So you're like, oh, we collided these protons and nothing appeared. Energy would seem to disappear. Energy wouldn't be conserved because the energy of the tachyon is now gone in time somewhere. Not causally related. It's left your light cone.
And that would be evidence of something destroying energy. Well, not destroying energy, but energy going into something we cannot see.
Yeah. And to some extent, that's what happens with neutrinos, right? We always produce a bit of neutrinos in these collisions, and neutrinos can escape at very, very, very high, very, very high percentages. They interact with almost nothing.
But they have mass.
They have mass, so we see a small decrease in energy. It looks like a bit of energy is lost when actually it's been carried away by neutrinos and we can't see them.
No, but wait a second.
We can't conclude from the loss of energy what kind of particle is responsible for it.
Well, that's also because we can detect neutrinos if we try really, really hard in other experiments, right? So first we detect them in other experiments, so we know how many there are, and you know what their masses are, or you try to know what their masses are, and then from there you see, oh, exactly this amount of mass has gone missing. I guess that corresponds to 2 neutrinos.
Yeah,
and then you can work out the maths.
We briefly mentioned neutrinos last time, but I'm not sure I got correctly what you said, because if neutrinos have mass, and during those collisions, some energy is taken away by this mass of neutrinos, why would energy disappear in the case of tachyons if they have negative mass? Energy should increase.
They travel faster than light, so they would leave your light cone. You would have no way of seeing them. They've left. So in general relativity,
if mass is energy, negative mass is negative energy. So why would they take away energy if they have negative mass?
It's because mass traveling forward in time, when you change the sign of the time, you have to change the sign in front of the mass. It's a technicality. We don't know what it really means. At the point of decay, energy would still go into that mass, except that mass would be negative because we see it. Well, we write it down going backwards, so you have to flip the sign. It's a mystery, to be fair.
So it works in maths, but you don't really know what it means in practice.
You can speculate.
Yeah, no, of course we can speculate. I was just wondering that, I mean, the math of it works. It's just that our brain can't really picture how it would look like or why it would be like that. It just works on paper.
It works on paper.
Okay. But it's pretty much impossible to prove in practice. At least for now, I guess. Oh,
first, we need to have better model of particle physics, I guess. But there is also they can be made to fit in particle physics, but there's no need for them either. It's just like a strange curiosity that seems to be permitted, but not happening in practice, like a lot of things are in physics.
Okay. I see someone typing a question. We are out of time, but I'm just going to take another brief one, which is not entirely related to time, but somewhat. So I'm going to take it anyway. It is about black holes, and Commander Busty Wonder is asking in our galaxy, the galaxy of Elite Dangerous, when we go near the exclusion zone of the black holes, shouldn't we actually experience time dilations? Because we are being influenced by gravity, we can get pretty close to black holes
Yep.
With our ships, but we don't really start experiencing time in a different
Yep.
way
The
than
answer
others.
is yes. Yes, you would. You would feel time differently. You definitely would. If you get to the point that the black hole can kill you, you would definitely have noticed a lot of time dilation by then.
Also, you would have noticed being dead, but
And looking out from the black hole, looking away from it when you're really close to that point, you would see things very differently too. Everything would have higher energy, your ship would take damage from accelerated visible light that will become UV.
well, our ships take damage when we go near black holes. However, when we look out of it, we just see a lot of distorted stuff. We just see other stars, galaxy, nebulae that are far away and distorted and curved. But what do you mean by higher energy? Like brighter stuff? We would see.
Yeah, you would have you'd have a gravitational bending effect where everything would look brighter to you and you would look fainter to someone outside. So if someone could wait for you away from the black hole and you got really close and they were somehow zooming on you, you would start to change color. You'd become red and more red as you approach the event horizon.
Okay.
I cannot hear Craig anymore because my computer crashed.
Yeah, Craig is our artificial intelligence.
Or Michael.
He
I cannot hear anyone on the Discord
Yeah,
chat anymore.
He's not actually a person, so don't worry.
Craig is
I've
just
lost
the
my
recording.
headphones because my computer's dead.
Okay. You need to call the hull seals for that if your ship has a breach. But anyway.
Well, this is your ship, Nightfall.
Oh shit, you're right. Well, why am I still talking then? Okay, we'll figure this out later.
Running out of fuel, I guess.
Anyway, yeah, we have another question. I'm going to read this. This is probably going to be the last one for tonight. From Brendockle. Let me read it. This seems quite specific. What about the case of the Alcubierre drive? I'm not sure what that is. He says, okay, he means bending the fabric of space in front of and behind a spaceship. From the perspective of the pilot, how would time behave? So this is basically Star Trek, right? This is what Star Trek does. Maybe. No.
Yeah, probably.
No, wait.
I mean, it's the most common theoretical warp drive design.
Okay. Well, he's saying that technically the ship does not experience velocity.
Mm-hmm.
The pilot is just swimming forward through space with a speed that the pilot observes as faster than light travel. What would time to his personal time?
What would you do to his personal time? Nothing. You'd be fine. Your clock wouldn't run behind galaxy time, if that's your question. If what we discussed before, if we define something like galaxy time, which is very far away from all sources of gravity, where space-time is as close to being flat as possible, then if you design your Alcubierre drive properly, and that means, without glitches or leftover bending in the center, or any of those bad manufacturing defects that happen sometimes in our galaxy, if your Alcubierre drive was designed properly, the center is just equally flat. So your passage of time is the same, is the passage of time in the absence of curvature. So you as the pilot wouldn't experience anything strange as far as time is concerned. And when you emerge at your destination, your clock, if you've done things properly, would still be in sync with galaxy time. Now, what you would see while you are traveling in your Alcubierre drive and the space in front of you is dilated or compressed in front or sideways, depending on what version you're using, what you would see is a much bigger problem. Because if you are running into photons, say from stars in front of you, as you are moving towards them at faster than the speed of light, but those photons are not traveling on the surface of space-time faster than the speed of light compared to you. They're still traveling at the speed of light compared to you. But what happens to the frequency of those photons is what can be deadly. So if you're not careful and you bend space-time wrong, you are going to end up blue shifting these photons very much. Even though they're still going at the same speed compared to you, they will be so blue shifted that you'll basically be running into a bunch of gamma rays. So what used to be nice and happy stars in front of you, their
now
light will be
lasers.
blue shifted. They're now lasers.
Okay.
So you have to be very careful exactly how you do your space-time bending and how much shielding you're going to need. Yep.
Huh.
Would that allow steering though, or is it just a straight line?
You could steer in some versions of the Akubi air drive, but depending on how you do your bending. But yeah, you could.
Because I was wondering, maybe that's how the FSD works.
I don't think so.
It
I
is
think the
influenced by
FSD
gravity,
bends
so-
points of space-time together. So it's a jump.
Yeah, and the
Jump
FSD
drive.
is influenced by gravity, so the theoretical model of the drive would have to explain that too.
Yeah, true. True. Okay. Okay, well that was great. We don't currently have any more questions. I'm checking both the distant radio channel or the astronomy channel in Fleetcom.
Yeah, I'm about
So-
to land my ship, so if you want, you can wrap up things up.
Yeah. It's been more or less an hour. We ran out of questions, so I believe that this will be it for tonight. And next time, I think we will handle quantum physics, because
Oh,
this
okay.
seems to be a
Quantum
topic
mechanics.
that quantum physics, quantum mechanics. What's the difference?
I don't
Huge.
know.
Huge. Okay, well, we will leave that question for next week. We will explain what quantum mechanics / physics is, what's the difference, and there's a lot to disentangle from quantum mechanics. I just know the very basics, and I am interested myself in
Pun
learning a
intended.
bit more. So yeah, indeed, maybe we can make a show about GR even. Just to no, you don't
That's
like that.
pushing it a bit far from what I work with.
Okay. Just an idea, you know.
GR is one of these things that you cannot get an instinct for, no matter how hard you study and how much you think you understand it. You have to go back to the maths because it is counterintuitive more often than it is intuitive.
I was expecting quantum mechanics to be less intuitive than GR, but
Maybe to some people, but not to me.
Okay, I guess that when you
GR
get
is hella confusing.
If you compare GR to quantum mechanics, I think yes, quantum mechanics makes less sense than GR on an intuitive base, but still both.
I guess when you get deep into it, into the actual equations and things, it gets much more complex than what we usually know without working on it.
And then, but then you have quantum field theory, and that beats both by a mile.
And we will have a show about that.
No, please, no, God.
What do you mean no? We're making science here. How about string theory?
No one can explain quantum field theory without referring to
about
maths. No one.
quantum
I've never
gravity?
seen anyone do it, no matter how gifted they have been.
Okay.
Quantum field theory is a complicated monster.
Well,
but it works, so we love it. It makes no sense, though.
Okay, it makes no sense, but it works. All right.
It explains a lot of stuff.
Yeah, well, it will have to eventually if we want to understand this universe more and more. But yeah, this will be it for tonight, guys. Thank you for tuning in. This has been Nightfall Zero with that Michael and, of course, our guest, Dr. Sarah, also known as Commander Shoba. If you guys want to re-listen to this stream or watch the Twitch stream that Michael uploaded, Michael handled, both will be uploaded somewhere. I'm not sure where Michael is uploading them, but they will be rebroadcasted.
Yes, that also.
The video will be available on Twitch, as with all the previous, well, not the previous one, because we had no stream, but we have the audio file for that. I'm not sure if it was rebroadcasted.
I will share links to those audio files because I'm uploading those to hearthis.at.
Okay.
just so
Okay.
everyone
Cool.
can listen to it, and also you can add those to your podcast applications of choice, and they will update automatically.
Great. Great. Just as a reminder, Shoba also usually writes articles weekly on the Distant Worlds 2 newsletter. Last week, the newsletter was a bit shorter than usual, so there was no article from her, but there's, I think, 3 at the moment uploaded in the first 3 newsletters, and she plans to write more, right?
Yep,
Do you
there's
have
a
any
good
idea?
one coming next time.
Really? What is it about?
White dwarves.
White dwarfs. That's the bane of everyone in Elite. Trying
Oh.
to
Yeah,
trying
the
to
Shining Dead.
What if I told you this cool fact?
Don't spoil.
No,
Leave
but
it-
I only learned this today. I was chatting with a friend who works on White Dwarfs, and he told me apparently, by the latest counts, either M stars or White Dwarfs are competing for the most common type of star in the galaxy.
Wait, no, that's not
Yeah,
true.
because every giant star that ever died has become a white dwarf, and there have been a lot of them. We already know, just quite nearby to Sol, 250,000 of them. They are insanely common and very scary.
I just changed
All
my
right.
mind about space travel. I just gonna stay at home. I
Well,
don't want white dwarfed.
well, people try to. Oh, hey, I can just use that neutron star to get to to put my FSD in overdrive mode. I'll do it the same with the white dwarf. It's going to be easy, right? Next time you are calling the hull seals because they're just yeah. White dwarfs in Elite are something we should avoid as much as possible. I'm not sure if they are as
they're not
dangerous as
worth
neutron
it.
stars in terms of in actual.
Nope.
Nope.
Nope. They are friendlier than neutron stars.
Well, if you want to know more, you will have to wait for the article. And of course, if you have questions about articles, both past and upcoming, feel free to drop questions as well. We will answer them. Well, not us. Shoba will answer them. And if you're also interested in something a bit more sciencey in terms of writing style, the personal website of our doctor is available as a pinned message, I believe, in one of the Distant Radio channels. I think it's in Radio Chatter,
In
maybe?
the Radio Chatter, yeah. It's in the
Exactly.
Radio
And you
Chatter
can
channel.
find her personal website there with the papers that she published
And the TLDR,
of the papers.
of my research
Okay.
and some
Yeah.
of the papers.
Yeah, in case you guys are listening to this for the first time and you are not sure who this Commander Shoba is and what her credentials are,
It's all right.
we are not going to repeat them every time. So if you guys don't know yet who she is, just feel free to check her website so that you can see for yourself that she is qualified to talk about what we are talking about.
And if you want to see me IRL and you're in the UK, I will be in Durham on the 21st of February and in London in April at some point. It should be on my website.
Is it free?
Yep.
Cool. So if you want some more free science and you are around and you have some free time, and if you're interested, feel free to contact either the staff of Distant Radio or even her directly on Discord.
Oh yeah, if people are in London and they want to go to the pub, I will not say no, as a rule.
Or that. So that's just more chances to talk about science, so you should grab the opportunity. Thank you again, guys. Yeah, thank you, Michael, for hosting this.
Thank you, Michael. Sorry for not hearing you over the last 10 minutes.
Yeah, I'll have to fix my shit. Yeah, no, it's all right. And of course, thank you, Sarah, for joining us tonight. I know that you're busy. I know that you're tired. But you always take time for Distant Radio.
Oh, it's fun. Don't worry.
Worlds. So thank you. Thank you for that. I think everyone here and our listeners appreciate it. So this has been Nightfall Zero, live from the Red Comet. And this has been Distant Radio 3305. I will see you.
This was dangerous. this was dangerous cosmology.
Indeed.
Oh.
Dangerous cosmology. Very dangerous. Very cosmology. Wow. So much space. Very space. Much danger.
Wonderful.
Very White Dwarfs.
Yeah,
And all
don't
of
forget
that.
to tune back in next week, and also stay tuned into
I'm
the radio all the
face-palming
time,
to be
because I hate you otherwise.
Yeah, I'm not sure if there's anything after us. I don't know.
Not for a while, but Auto DJ will be happy to entertain you guys.
Cool. Great. So thank you again for tuning in, guys. I will see you next time, and maybe in the black out there as we head together to Waypoint 4. Bye-bye.
Stay safe out there. Bye bye.